13.8 billion years. That number is carved into every textbook as the absolute age of everything. But the James Webb Space Telescope just sent back data that proves it wrong. It found impossible galaxies, massive giants existing when the universe was supposed to be a mere infant. We aren't talking about a small calculation error here. New evidence suggests our universe is actually 26.7 billion years old. Before we rewrite reality, hit that like button and subscribe, because the history of our universe is about to change forever. Prepare yourselves. We begin. Imagine peering through the ultimate time machine, back to when the universe was barely out of diapers, just 500 to 700 million years old. A cosmic toddler stumbling around in the dark. And that's exactly what the James Webb Space Telescope did when it unfolded its golden mirrors 1 million miles from Earth in December 2021, expecting to catch the first flickering baby galaxies, those puny dwarf clumps with maybe 100 million stars each, fragile little things. Gravity was just starting to knit together, but instead it spotted 6 blazing red dots that screamed impossibility, bright crimson beasts, in a patch of sky near the Big Dipper, where old Hubble had seen squat. Yet Webb's infrared eyes pierced the stretched light of billions of years, revealing objects with red shifts so extreme they dated to cosmic dawn. And when the team crunched the numbers, jaws dropped, because these weren't newborns. They packed tens of billions of stars apiece, some rivaling the Milky Way's heft that took 13 billion years to bulk up. And a University of Colorado Boulder expert blurted it out plain: you just don't expect the early universe to organize itself that fast. These galaxies shouldn't have had time to form under any rules we know. Picture the math breaking right there. Stars don't pop into being like magic tricks. Gas clouds have to chill out, clump under gravity's tug, spark fusion in their hearts, a process that crawls. Our own Milky Way squeezes out just 2 fresh stars a year. So to balloon these monsters in 700 million years, they'd need hundreds, birthed annually non-stop. And even that strains credibility. Worse yet, the early cosmos ran on hydrogen and helium alone. No heavy elements to grease the wheels of big galaxy building. Those came later from star guts exploding. Yet these rebels sidestepped every barrier, defying the brutal physics like they owned a cheat code. Then the weirdness piled on. Some galaxies looked pint-sized, but outweighed sprawlier neighbors, flipping evolution's script, where mass sprawls big over eons. These were dense-packed titans, squeezing Milky Way mass into pinky nail volumes. Gravity should have crushed or ignited them wild, but nah, they thrived serene. And enter the real showstoppers, the 3 red monsters, ultra-massive bruisers from the first billion years, glowing ruby in Webb's gaze, thanks to dust veils, gobbling blue light, and spitting red, courtesy of an international crew from Geneva University, who sifted the fresco survey data on 36 dusty star factories with red shifts 5 to 9, when the universe clocked 1 to 1.5 billion years, most fit the baby mold. But these 3 outliers converted gas to stars at 50% efficiency or higher, double or triple today's 20%. Norm churning hundreds of billions of stars like Milky Way twins. Lead author Menjuan Zhao nailed it. Our findings reshape early galaxy formation, and no active black hole nuclei lit them up falsely. No quasar tricks, just raw stellar fury from conditions we can't grasp. Maybe denser gas cooled quicker, or feedback winds failed to stall the frenzy. These weren't flukes. Webb cataloged hundreds more in cosmic evolution surveys, over 250, between 800 million and 1.5 billion years. Post-bang, many sporting mature disks, bulges, even spiral arms that demand billions of mergers and spins. 1/10 the time our galaxy took for its elegant twist, obliterating slow clump models where dark matter halos scaffolded puny bits into giants over ages. Instead, the dawn teemed with adults, strutting like they partied through puberty, and explanations flew wild. Black holes faking mass via glow, but halved estimates still dwarf timelines, or top-heavy star births with giant short-lifers boosting shine. Yet those burn out fast. Cycles should have dimmed the blaze over hundreds of millions of years. But it roared steady, no active feeders in many, pristine starlight, pure and punishing. Dive deeper. These compact crushers dodged quench, where tight gravity should have scorched gas dry and silenced births. But they partied on, stars popping like fireworks, hinting gravity, or cooling played looser back then, and the dust shroud, that red hallmark, hid furious nurseries from optical scopes like Hubble, but Webb sliced through, unveiling efficiency monsters that laughed at waste. Newborn giants, blasting winds to scatter gas usually, yet here feedback flopped. Supernovae, from first fat stars, should have wrecked the joint early, but somehow the monsters muscled past, growing at rates, shredding feedback physics, screaming either alien rules ruled dawn, or ages lied, granting extra epochs to bulk up legit. Teams scrambled global. Yale crews marveled at the trio's star rates. Twice peers, Bath astronomers, dubbed them enigmatic. Live science puzzled their size surge. Earth.com hailed a new era's dawn, and Space.com stressed no AGN cheats, pure galaxy grit. While Times of India buzzed the reveal, SciTech Daily probed the mystery, all converging on turmoil. Our Lambda CDM tale of tidy timed growth, cracking under crimson weight. Because if standard clocks tick 13.8 billion, these beasts bust it, demanding rewind or stretch. And whispers grew, what if not too grand for youth, but perfect for doubled years? 26.7 billion, letting 1 billion plus for forging instead of half, easing frenzy to feasible, pressure popping like overfilled balloons. The wildfire spread subtle, papers swapped impossible for challenging, unexpected outliers, hedging bets. Webb piled dozens more red mature marauders, blobs belying billion-star bulks, turbulent most, but fractions flaunting grown-up gears, rotating calm, central swells from grav dances, demanding deep time, stats shredding fluke claims, hundreds hollering model meltdown, dark scaffolds, meant for inching merges, rush to rush hour jams, Milky Way's 10 billion year polish in 1 billion's blink, Geneva's monsters, mere poster kids for the plague, each 100 billion sun masses strong, dust-shrouded speed demons, birthing stars at 2-3 times later, paces, conditions cryptic, gas plenty cooling swift or unknown sparks, future Alma and Webb peaks, promising piles more. Xiao vowed they kick off fresh epoch hunts. And yeah, the universe's first billion brimmed, not barren, but beastly, rewriting dawn from dim sparkles to scarlet stampede, humbling hubris, as these monsters mock our maps, forcing gaze shift from formation fails to timeline treason. Because if physics held firm, the clock caved, and that glitch gleams bigger than any galaxy, teasing truths that twist all we thought solid. But hold tight, the monsters are just appetizers. Next up, a backyard star, older than existence itself, shattering skies closer to home. For nearly a century, scientists have been wrestling with one massive question: how old is everything? And the number they landed on, 13.8 billion years, didn't just fall out of thin air, but came from measuring the universe's expansion rate, observing the oldest stars, and analyzing radiation left over from the Big Bang itself. And this age became cosmology's bedrock, appearing in every textbook, while every model of cosmic evolution built from it like a foundation stone. But the path to this number was messier than most people realize, and the cracks in its foundation have been lurking there from the very start, waiting to split wide open. The story kicks off in the 1920s with Edwin Hubble, who used the most powerful telescope of his era to measure light from distant galaxies, and noticed something shocking. The light was redshifted, stretched toward longer wavelengths, like a cosmic rubber band pulled tight, and the farther the galaxy sat, the more its light shifted, following a clear pattern where more distant galaxies moved away faster, with their light stretched more by the expansion of space itself. And Hubble realized in that moment the universe wasn't some static frozen picture, but a growing, expanding thing. And if you run that expansion backward in time, like rewinding a movie, everything must have been squashed together at a single point, which became known as the Big Bang. But knowing the universe is expanding doesn't immediately hand you its age, because you need to measure how fast it's expanding, that rate called the Hubble constant. And measuring it turned into one of astronomy's biggest headaches, with early estimates varying wildly. When the Hubble Space Telescope launched in the 1990s, scientists thought the universe might be anywhere from 7 billion to 20 billion years old, a range bigger than Earth's entire age. And the uncertainty came from the brutal difficulty of measuring cosmic distances accurately, where a small error in distance translates to a massive error in age. But by the early 2000s, new techniques and better telescopes narrowed the range as scientists used observations of Type 1a supernovae, exploding stars that shine with consistent brightness, like cosmic light bulbs. And by measuring how dim these supernovae appeared, astronomers calculated their distance, combining thousands of measurements across cosmic history to refine the expansion rate bit by bit. Another breakthrough came from studying the cosmic microwave background, that faint radiation left over from when the universe was only 380,000 years old. A baby snapshot frozen in time, and the European Planck satellite mapped this radiation with incredible precision, revealing tiny temperature fluctuations that encode information about the universe's age, composition, and fate, like a cosmic birth certificate. And all the methods converged on the same answer: 13.797 billion years, give or take 23 million years, an uncertainty of less than 1%, which seemed like cosmology had finally nailed down its most important number. The Lambda CDM model, our standard picture of cosmic evolution, incorporated this age and explained how matter clumped into galaxies, how the cosmic microwave background formed, how light elements were created in the Big Bang's first minutes, and everything fit together into an elegant story where the universe began in a hot, dense state, expanded and cooled, stars formed, galaxies grew, and here we are 13.8 billion years later, living in the aftermath. But even as this consensus formed, troubling observations accumulated like storm clouds on the horizon, because some measurements of the Hubble constant using nearby galaxies suggested a faster expansion rate than the cosmic microwave background predicted. And a faster expansion means less time has passed, implying a younger universe, with some estimates dropping the age to as low as 11.4 billion years, while others pushed it to 12.7 billion. And this became known as the Hubble tension, a growing disagreement between different measurement methods that refuses to go away and isn't just an error, but a real discrepancy, suggesting something in our model is incomplete or broken. Then there are the stars. Globular clusters in our own Milky Way galaxy contain some of the oldest stars in existence, ancient veterans that formed early before the galaxy fully took shape. And by studying the brightness, temperature, and chemical composition of their stars, astronomers can estimate ages, with most cluster stars coming out to around 12 to 13 billion years old, which seems reasonable given the universe's age. But a few stars push the limits uncomfortably, appearing to be as old or older than the universe they inhabit, which should be impossible because an object can't exist before the container that holds it. It's like finding a fossil older than Earth itself. And the most famous case is a star called Methuselah, catalogued as HD 140283, located just 200 light-years away, close enough to study in detail. And this star presented a mathematical nightmare, because its low metal content indicates extreme age, where metals in astronomy terms means any element heavier than hydrogen and helium. And the early universe had almost no metals, since they had to be created inside stars and scattered by supernovae. So low metal stars formed early before much metal existed, and Methuselah's metal content is 1/250th that of our solar system, making it ancient beyond belief. Measurements of Methuselah's age kept coming back wrong with early estimates, placing it at 16 billion years old. Later refinements, using Hubble Space Telescope data, reduced that to 14.5 billion years, plus or minus 800 million years. And even with the uncertainty, the star's most likely age exceeded the universe's calculated age, so astronomers reassured the public that the error bars overlapped, meaning technically there was no contradiction. But the fact that the central estimate kept coming back older than cosmic time bothered everyone like a splinter under the skin, and more recent models have adjusted the star's age downward to somewhere between 12 and 14 billion years, making the paradox seem resolved, except it really wasn't. It just got hidden in uncertainty ranges and wishful thinking. These weren't isolated problems, but symptoms of something deeper, because the 13.8 billion year age worked mathematically, satisfying the equations of general relativity and matching most observations of the cosmic microwave background. But it required the universe to be incredibly efficient at forming structures where galaxies had to assemble fast. Stars had to ignite early. Everything needed to happen on a tight schedule, like a cosmic assembly line running at max speed. And when James Webb looked back and found mature galaxies and massive structures already in place, at cosmic dawn, the schedule broke. There wasn't enough time. The universe was operating ahead of the timeline. We gave it like a student, finishing a 4-year degree in 2 years, which suggests either the student is superhuman or the timeline is wrong. And perhaps because the timeline itself was wrong all along, the deeper James Webb looked into the cosmic past, the more impossible the universe became, because after the initial 6 massive galaxies shocked astronomers, the telescope kept finding more. Dozens of bright red mature structures existing in the first billion years. Some appeared as mere blobs of light, but their properties revealed ages and masses that defied explanation. And these weren't anomalies scattered here and there, but everywhere you looked, the early universe was packed with fully developed galaxies that standard cosmology said should be tiny blue baby systems, just beginning their lives, fumbling around in the dark, trying to figure out how gravity works. One team analyzing Webb data from the Cosmic Evolution Early Release Science Survey cataloged over 250 young galaxies existing between 800 million and 1.5 billion years after the Big Bang, and most were turbulent, clumpy systems, which matched expectations because the early universe should be messy with gas puffed up and moving in all directions, according to research from Cambridge University, published in monthly notices of the Royal Astronomical Society. But a significant fraction showed organized structures, rotating disks, central bulges, features that take billions of years to develop through gravitational interactions and mergers. And finding 1 or 2 precocious galaxies could be explained as statistical flukes, weird outliers that got lucky. But finding hundreds suggested a systematic problem with the models, where the numbers didn't just barely exceed predictions, but obliterated them like a wrecking ball through a glass house. Standard theory suggests that matter in the early universe clumped together slowly, where dark matter halos formed first as invisible scaffolds of gravity, and regular matter fell into these halos, cooled, and eventually condensed into stars in a gradual process where small structures merged into larger ones over billions of years. and our Milky Way formed through countless mergers of smaller galaxies, with its spiral shape and organized disk structure, taking 10 billion years to develop through patient cosmic choreography. But Webb was showing galaxies with similar features existing when the universe was less than 1 billion years old. They had 1/10 the time, but looked just as mature, sporting disk structures and spiral patterns that shouldn't exist yet, according to everything we thought we knew. Meanwhile, other discoveries deepened the crisis, because astronomers found a superheated star factory galaxy known as Y1 existing just 800 million years after the Big Bang. And this galaxy was birthing stars at a rate 180 times faster than the Milky Way does today, according to research using the Atacama Large Millimeter Array. And such intense starburst periods might have been common in early galaxies, but the sheer speed challenges our understanding of how quickly gas can cool collapse and ignite fusion. And even more troubling, Webb spotted supermassive black holes in galaxies just 570 million years after the Big Bang, as reported in Nature Communications in November 2025. And these black holes were overmassive compared to their host galaxy's stellar mass, suggesting that black holes in the early universe grew much faster than the galaxies that hosted them, which flips our models on their head, because we thought galaxies grew first and black holes followed. But here, the black holes led the charge. The timeline pressure became unbearable because every new observation from Webb added another impossible object to the list, another galaxy that shouldn't exist, another star too old, another black hole too massive, and teams worldwide scrambled to explain it, proposing that maybe stars formed faster in the early universe because it was denser, making it harder for gas to blow away during star birth, which is possible, but the effect would need to be extreme to match observations. Or maybe the initial mass function was different, with more massive stars forming, which would boost brightness, but those stars die quickly, so the effect fades, and none of these band-aid solutions truly fix the bleeding wound at the heart of cosmology, which is that 13.8 billion years simply isn't enough time for everything we're seeing. Some researchers started whispering the unthinkable. What if the galaxies aren't too big? What if the universe isn't too young? What if our most fundamental assumption about cosmic age is wrong by a factor of 2, and the James Webb revelations didn't just show us distant galaxies, but showed us a universe that doesn't fit inside 13.8 billion years? Something fundamental has to give. Either the physics of star formation is completely alien in the early cosmos operating under rules we don't understand, or time itself is longer than we thought, stretching back not 13.8 billion years, but much, much further. And as more data poured in from Webb, the second option started looking less crazy and more necessary, because when you eliminate the impossible, whatever remains, however improbable, must be the truth. And the truth staring astronomers in the face is that the cosmic clock might be ticking in double time. The universe might be twice as old as every textbook claims. And if that's true, then everything we thought we knew about cosmic history needs to be rewritten from scratch. But there's more evidence beyond these galaxies, and it gets even stranger, because right here, in our cosmic backyard, floating just 200 light years away, there's a star that might just prove the universe is older than time itself. Floating just a little less than 200 light years from Earth, there is a star with a story so strange it has haunted astronomers for decades. A sun that seems to exist outside the very bounds of cosmic possibility, and its official name is HD 140283. But everybody knows it as the Methuselah Star, a nod to the ancient biblical patriarch whose legendary age signaled wisdom and survival far beyond the ordinary. So it is fitting that this particular member of our galaxy carries a number that even the universe itself cannot easily explain. The Methuselah Star is a population 2 star, one of those ancient survivors formed before the Milky Way grew to maturity. And while nobody questions its antiquity, The numbers just do not add up. Or maybe they add up in a way that rips up every cosmology textbook. To find the age of such a star, astronomers use a forensic toolkit, combining its luminosity, the color and temperature revealed by its light, its physical distance from Earth, and above all, its chemical fingerprint, because metal-poor stars, those that lack elements heavier than hydrogen and helium, can only be formed in the very earliest eras of the universe, before stellar explosions from supernovae enriched the cosmic soup with heavier stuff. Methuselah is about 1/250th as metal-rich as our own sun, an astronomical signal flare shouting, "I was born early," when the cosmos was young and unadorned. Early attempts to calculate its age set it at a gobsmacking 16 billion years, and even today, the best estimates, after careful observation by the Hubble Space Telescope and work by teams around the world, hover close to 14.5 billion years, with a margin of error still stretching either side of the accepted cosmic age, which is supposed to be 13.8 billion years. While it is tempting to dismiss this as a mistake, or a mere artifact of uncertainty and error bars, because the estimated age for the universe itself has been refined using several methods, from mapping the cosmic microwave background to observing the faint flickers of distant galaxies. The tension remains, and in scientific culture, tension is usually where the most interesting physics is hiding. For a while, the easiest excuse was that something must be off in the stellar physics. Maybe the calculations did not account perfectly for the way elements diffuse from the surface to the core, or perhaps the star's distance was marginally miscalculated, throwing off the model of its brightness, and therefore its true age. But as instrumentation improved, notably with the precision of Hubble's parallax measurements, the central figure for the age of Methuselah stubbornly refused to move much below 14 billion years. The real heartburn comes when you realize the uncertainty for the star's age, about 800 million years, overlaps, but does not dissolve the paradox. That is, it is technically possible Methuselah is younger than the universe, yet equally likely it is older, and it is this razor's edge that leaves so many cosmologists awake at night. This single anomaly becomes more than a footnote when placed beside similar relics studied in the hearts of ancient globular clusters, collections of stars as old as time itself, many of which also appear dangerously close to, or even older than the canonical age of the universe. According to the strict math of stellar evolution, these ancient stars are the high court evidence contradicting the neat timeline of cosmic history that says everything started at a single moment, expanded, cooled, and gradually evolved stars and galaxies over 13 billion years. Methuselah's measurements say otherwise, daring us to consider maybe the universe is actually older. Recently, radical thinkers have moved this story to the front page of Cosmology, such as physicist Rajendra Gupta in 2023, who published a model suggesting that the universe might in fact be 26.7 billion years old, nearly double the old estimate, and suddenly Methuselah and its kind look entirely reasonable, their ancient glow no longer a crisis, but a clue. Yet the debate is heated, and many experts point to the multitude of measurements, the cosmic microwave background, the expansion rate pinned down by supernovae and distant galaxies, the large-scale structure, maps etched across the heavens, that all coalesce elegantly around the 13 billion year mark. So any outlier, even a particularly well-studied one, like Methuselah, is subjected to immense scrutiny and debate. But whether it is a quirk of physics, a loophole in the models, or a genuine sign the universe's calendar is off by aeons, Methuselah stands as a cosmic detective, a time traveler, reminding us that even as our tools become sharper and our equations tighter, the universe refuses to be boxed in by our presumptions. This old star is proof that the universe still holds secrets, its faint light, a glowing testament that sometimes the answer to the most fundamental questions about reality is lurking, not in fantastically distant galaxies or strange quantum lands, but right in our own celestial backyard, quietly violating the rules we thought were unbreakable. and inviting the boldest minds to look deeper, challenge convention, maybe, just maybe, rewrite the story of time itself. JWST. The 26.7 billion year theory explodes into the cosmic scene like a supernova, driven by the bold calculations and fearless questions of physicist Rajendra Gupta, who dared to challenge the accepted cosmological calendar and forced everyone to rethink the chronology of existence itself. So let's drop straight into the heart of the model that could rewrite every science textbook on your shelf and transform our understanding of how the universe evolved from its first breath to the present moment. At its core, Gupta's reimagined universe is not just an incremental tweak of numbers or a minor adjustment to some obscure equation buried in the footnotes of an astrophysics journal, but a fundamental rethink of how light travels across cosmic oceans and how the unchanging laws of physics may have slowly morphed as the universe matured through its infancy, adolescence, and eventual adulthood. It is here in this intersection of new observation with old mysteries that Gupta conjures his answer to why galaxies appear impossibly old, and why stars like Methuselah refuse to fit inside the 13.8 billion year box that cosmologists have been trying to squeeze them into for decades. Gupta resurrected a long-discarded idea called tired light, first proposed by Swiss astronomer Fritz Zwicky way back in 1929, which says photons lose a tiny bit of energy as they cross the emptiness between galaxies, becoming redder not just because space itself is stretching out like a cosmic balloon inflating, but also because the photons gradually tire from their epic journey across billions of light years, shedding energy bit by bit through mechanisms that mainstream cosmology had rejected. Alone, tired light was thrown out by astronomers decades ago, since it could not explain the cosmic microwave background, that faint afterglow of the Big Bang that fills the entire sky with ancient radiation, nor could it account for the time dilation witnessed in distant supernovae, where explosions that should unfold over weeks appear to stretch over months when viewed from across the cosmos. But Gupta's twist is to combine tired light with the traditional expanding universe paradigm, allowing both mechanisms to affect the redshift astronomers measure in faraway galaxies, creating what he calls a hybrid phenomenon. Instead of interpreting every wavelength stretch as rapid cosmic expansion racing away from us at breakneck speeds, Gupta splits the blame between space swelling and photon fatigue, arguing that this hybrid model extends the universe's true age, because if only part of the redshift comes from expansion, then galaxies aren't as far away or as young as we thought, and by factoring in both tired light and the classical expansion, galaxies once thought to be impossibly young, those red monsters packed with hundreds of billions of stars, existing just 700 million years after the Big Bang, suddenly snap into place, because with a doubled timeline, they have plenty of epochs to grow, to merge, to assemble their spiral arms and central bulges, to birth generations of stars, and scatter heavy elements across their disks, no longer violating physics or straining credibility to the breaking point. To unlock even more time and make the math work across multiple independent observations, Gupta borrows another radical idea from the 20th century physicist Paul Dirac, one of the founding fathers of quantum mechanics, who revolutionized our understanding of subatomic reality. And Dirac mused way back in 1937 that nature's most fundamental constants, those numbers that regulate how strong gravity tugs, how fast light moves through the vacuum, or how electrons dance in their atomic orbits, might not be as constant as we imagine, possibly evolving over billions of years as the universe itself evolved. And this idea was largely ignored for decades, because it seemed unnecessary and difficult to test. If the coupling constants that shape atomic transitions and cosmic interactions are allowed to shift even a little bit over cosmic time, it could expand the available window in which the universe forms complex structures, stretching the story of cosmic evolution by billions of years, without breaking the elegant harmony of observational data we have painstakingly gathered from telescopes, both on Earth and in space. And Gupta specifically proposes that these constants vary in a coordinated way, what he calls covariant coupling constants, or CCC for short, where changes in the speed of light, Planck's constant, and the gravitational constant all shift together in such a manner that the atomic transitions we observe in distant galaxies still match our expectations, even though the underlying physics has subtly changed. Gupta adds to this mix a rethinking of the cosmological constant, that mathematical plug representing dark energy, which Einstein famously called his greatest blunder, but which modern cosmology embraced to explain why the universe's expansion is accelerating, and instead of treating it as a fixed immutable number, Gupta proposes a constant that accounts for the evolution of the coupling constants, allowing cosmic acceleration and structure formation to proceed hand in hand, all stitched together by the math of a revised cosmological model he calls CCC plus TL, combining covariant coupling constants with tired light in a framework that challenges the lambda CDM model, which has dominated cosmology for decades. When Gupta tested the hybrid model, expansion plus tired light plus evolving constants, against the distances and redshifts of Type 1, a supernovae observed across billions of light years, the cosmic microwave background mapped with exquisite precision by satellites like Planck and WMAP, and the densities and brightnesses of ancient galaxies now revealed in stunning detail by the James Webb Space Telescope. The fit was tight enough to suggest 26.7 billion years, makes everything finally hang together without the mathematical gymnastics and ad hoc explanations that plague the standard model. Suddenly, those mature galaxies sporting organized disks and massive stellar populations, those impossibly massive black holes lurking in the cores of infant galaxies, and ancient stars like Methuselah, which previously existed as anomalies and headaches that kept astronomers awake at night, now simply occupy their rightful chapters of an expanded cosmic timeline where they had sufficient time to form and evolve naturally. The theory even opens the door to explaining why small and compact galaxies could emerge so quickly in the early universe, why the first billion years were packed with so much action and activity, and why dark matter and dark energy might not be required in their traditional forms, if the universe's physical parameters have shifted over time, with Gupta even suggesting in follow-up work published in 2024 that dark matter might not exist at all, its effects merely illusions created by the varying coupling constants and tired light mechanisms altering how we interpret gravitational lensing and galaxy rotation curves. According to his calculations, published in the prestigious monthly notices of the Royal Astronomical Society, the newly devised model stretches galaxy formation time by several billion years, making the universe 26.7 billion years old, instead of 13.7 as previously estimated. And this isn't just speculation, but a rigorous mathematical framework tested against real observational data. His work suggests that at a redshift of z equals 10, corresponding to galaxies, near the edge of what James Webb can see, the universe would already be about 6 billion years old in his model, compared to just 400 million years in the standard lambda CDM framework, giving these early galaxies more than 10 times the amount of time to assemble their masses and develop their structures. And this extended timeline means star formation rates don't need to be absurdly high, feedback processes don't need to be mysteriously suppressed, and the physics of the early universe doesn't need to be radically different from today. But the story is far from settled, and the scientific community remains deeply divided. Critics warn that while Gupta's model cleverly solves the early galaxy problem revealed by James Webb, it must still survive the fire of the full cosmological gauntlet, matching not only galaxy formations, but also gravitational lensing maps, which trace how matter bends light across the universe, the arcane ripples of background radiation, which encode the density fluctuations of the infant cosmos, and the intricate distribution of matter on the grandest scales, where galaxy clusters and superclusters form cosmic webs stretching across hundreds of millions of light years. Some scientists point out that measurements from the Oklo Natural Nuclear Reactor in Gabon, where uranium underwent natural fission 1.7 billion years ago, constrain how much the fine structure constant could have changed over time to less than 0.3 parts in 10 quadrillion per year, billions of times stronger than what Gupta's varying fundamental constants would require, suggesting his model might violate known physics in ways we can actually test. Others argue that tired light predicts different surface brightness patterns for distant galaxies than expanding space does, and observations overwhelmingly favor expansion, while the cosmic microwave background's uniformity and black body spectrum are explained beautifully by the standard Big Bang expansion model, but not by tired light mechanisms, which would blur and distort the ancient photons. These aren't minor issues or technical quibbles that can be swept under the rug. They're fundamental tests that originally killed Zwicky's tired light theory nearly a century ago. And Gupta's response is that his model isn't pure tired light standing alone, but a small tired light contribution combined with expansion, where the expansion component handles most observations normally, while the tired light component just adds a correction that changes distance and age interpretations, tweaking the cosmic clock without completely rewriting the rulebook. Whether this delicate balance works depends on detailed calculations, future observations from Webb and other next-generation telescopes, like the extremely large telescope currently under construction in Chile, and the willingness of the scientific community to seriously entertain alternatives to the lambda CDM model, which has become so entrenched it's almost dogma. Still, by boldly rewriting the timeline and refusing to accept that the puzzles revealed by James Webb are merely anomalies or measurement errors, Gupta's 26.7 billion year hypothesis allows scientists to see the universe anew, no longer confined to the narrow corridor dictated by former models that were built on observations from less powerful telescopes and less complete datasets. In his hands, cosmology becomes a detective story where old clues are re-evaluated with fresh eyes. Ancient evidence from the cosmic dawn is reinterpreted through the lens of new physics, and the universe itself stretches open, vast and ancient, a stage where the mysteries of time, light, and matter are posed not just as riddles for mathematicians working in isolation, but as the next frontier for every curious mind who has ever gazed up at the night sky and wondered what came before the beginning, how old the stars truly are, and whether the cosmic clock we've been reading all these years has been running slow all along. Picture this: 1929, the roaring 20s winding down, jazz filling the air, flappers dancing in speakeasies, and in that same year, a Swiss astronomer named Fritz Zwicky, working at the California Institute of Technology, looked at the cosmic redshift that Edwin Hubble had just discovered and thought, wait a minute, what if there's another explanation entirely? What if light doesn't shift red because space is expanding, but because photons themselves are losing energy as they travel across the vast emptiness between galaxies, gradually tiring out like marathon runners, losing steam mile after mile? And Zwicky called this idea tired light, proposing that photons might interact with dust particles, gas clouds, or mysterious energy fields scattered through intergalactic space, each interaction sapping a tiny amount of energy, imperceptible over short distances, but accumulating into noticeable redshift after billions of light years. And in one stroke, Zwicky offered an alternative to the expanding universe that didn't require space itself to stretch or the cosmos to have a beginning point, allowing for a static eternal universe that had always existed and always would. For a while, tired light stood as a legitimate competitor to the Big Bang model, because in the early days, nobody had definitive proof that space was truly expanding. and the idea had intuitive appeal, since energy doesn't come from nowhere, and photons crossing cosmic voids for eons might naturally shed some of their oomph through encounters with matter or fields. And by the 1930s, more than a dozen physicists, astronomers, and even amateur scientists proposed various tired light mechanisms having in common the assumption that nebular photons interact with intergalactic matter, transferring part of their energy, with the term tired light itself actually coined by physicist Richard Tolman in the early 1930s, who used it somewhat mockingly to describe these alternative redshift explanations. But the name stuck and became the standard way to refer to Zwicky's hypothesis and its many variations. Zwicky himself was no slouch. The man went on to discover dark matter in 1933 when he used the virial theorem to study the Coma galaxy cluster and found that galaxies were moving so fast they should fly apart unless held together by some invisible gravitational mass at least 400 times greater than the visible matter. And he also predicted the existence of neutron stars and coined the term supernova to describe the catastrophic explosions that end massive stars' lives. So when Zwicky proposed tired light, he wasn't some fringe crackpot, but a brilliant physicist whose ideas deserved serious consideration. Zwicky acknowledged that any sort of scattering of light would blur the images of distant objects more than what telescopes actually observed, stars and galaxies remaining sharp and crisp even across billions of light years. But he pressed on refining the model and suggesting that perhaps the energy loss occurred through some non-scattering mechanism that wouldn't blur images, maybe through interactions with gravitational fields in what he called a gravitational analog of the Compton effect, or through photon gravitational drag, where the gravitational mass of photons calculated as h times nu divided by c squared would allow them to transfer momentum and energy to matter as they pass through space, meaning redshift should depend on the distribution of matter in space and vary with direction, which was a testable prediction. Zwicky carefully presented his proposals as falsifiable, according to later observations, noting that gravitational tired light should broaden absorption lines asymmetrically toward the red. And if these lines could be photographed with high enough dispersion, the displacement of the center of gravity of the line would give the redshift independent of the velocity of the system from which the light is emitted. And he also pointed out that according to tired light, a distance redshift relationship would necessarily be present, even in light from sources within our own galaxy. Even if the redshift would be so small, it would be hard to measure, predictions that don't appear under a recessional velocity-based theory, giving astronomers clear ways to test which model was correct. For decades, tired light lingered as a fringe alternative, attracting contrarians and iconoclasts who distrusted the Big Bang's implication of a cosmic creation moment, which seemed almost theological. And in 1935, Edwin Hubble himself, along with Richard Tolman, wrote that they both inclined to the opinion that if the redshift is not due to recessional motion, its explanation will probably involve some quite new physical principles, and discussed using a static Einstein model of the universe, combined with the assumption that photons emitted by a nebula lose energy on their journey to the observer by some unknown effect, which is linear with distance, and which leads to a decrease in frequency without appreciable transverse deflection, showing that even Hubble was open to tired light as late as the mid-1930s. In the early 1950s, physicist Erwin Finley Freundlich proposed redshift as the result of loss of energy by observed photons traversing a radiation field, and this was cited and argued for as an explanation for the redshift distance relation in a 1962 Nature paper by University of Manchester physics professor P. Marmot, who built on Freundlich's ideas. And even as late as 1986, a paper claiming tired light theories explained redshift better than cosmic expansion was published in the prestigious Astrophysical Journal, though 10 months later, In the same journal, such tired light models were shown to be inconsistent with extant observations, demonstrating that the theory refused to die quietly, even as evidence mounted against it. But by the 1960s, and especially after 1964, when Arno Penzias and Robert Wilson discovered the cosmic microwave background radiation, that faint 3-degree Kelvin glow filling the entire sky, tired light started dying. A slow death, because the cosmic microwave background had exactly the properties predicted by Big Bang expansion models. A perfect black-body spectrum, indicating it came from a hot, dense early universe that cooled as space expanded, and tired light couldn't explain why this radiation exists at all, or why it has such a uniform temperature across the sky, or why its spectrum matches theoretical predictions. So precisely, the observations simply didn't fit any tired light mechanism that had been proposed. The final nails in the coffin came from observations of distant supernovae in the 1990s and 2000s. Type 1a, exploding stars that serve as cosmic standard candles because they shine with consistent peak brightness, allowing astronomers to calculate distance by measuring how dim they appear. And astronomers measuring these supernovae noticed something crucial. Light from distant explosions appeared not just redder, but also stretched in time, the explosions unfolding in slow motion when viewed from billions of light years away, a phenomenon called time dilation that's predicted by expanding space. Because if space stretches while light travels to us, the light waves stretch too, and time stamps on those waves spread out, making the supernova appear to evolve more slowly. But tired light predicts no time dilation, because photons just lose energy without any temporal distortion, and observations matched expansion predictions perfectly with the time dilation factor, precisely equaling 1 plus the redshift as general relativity demands, while contradicting tired light completely. Another killer blow came from the Tolman surface brightness test, which showed that in a static tired light universe, the surface brightness of galaxies should remain constant with distance, because while distant galaxies appear dimmer, their apparent size also shrinks, keeping brightness per unit area the same. But in an expanding universe, surface brightness decreases with distance as 1/1 plus redshift to the 4th power, because recession causes both dimming and time dilation effects, and observations overwhelmingly favored the expanding universe prediction, with galaxy surface brightness dropping exactly as expansion models predicted, leaving tired light with no wiggle room. By the 1990s, tired light was declared dead and buried, relegated to the historical curiosities section of cosmology textbooks, alongside other failed theories like the steady-state universe, proposed by Fred Hoyle, which said the universe had no beginning and constantly created new matter to maintain constant density as it expanded, or geocentrism, which placed Earth at the center of everything, mentioned only to show students what doesn't work and to demonstrate how science progresses by eliminating wrong ideas through rigorous testing. And mainstream cosmology embraced the lambda CDM model with its expanding universe, dark matter accounting for 85% of all mass, dark energy driving accelerated expansion, and 13.8 billion year timeline as the unquestioned consensus framework taught in every university and appearing in every astronomy textbook. Yet Zwick's core insight that photons might lose energy through mechanisms beyond space expansion never completely disappeared from the fringes, and a small number of researchers continued exploring variations and modifications throughout the late 20th and early 21st centuries, asking whether tired light wasn't entirely wrong, but merely incomplete, whether both expansion and energy loss might occur simultaneously. And these fringe scientists faced ridicule and rejection from mainstream journals, who refused to publish their papers dismissing them as crackpot, attempts to revive a theory that observations had thoroughly falsified, but they persisted, driven by the conviction that something was missing from the standard model, that dark matter and dark energy were just placeholder names for our ignorance, and that the universe's true age might be hidden behind faulty assumptions about how light travels across cosmic distances. Then came July 2023, when Rajendra Gupta, an adjunct professor of physics at the University of Ottawa, published his bombshell paper titled Testing JWST, Early Universe Observations Against DCDM Cosmology in Monthly Notices of the Royal Astronomical Society, a highly respected peer-reviewed journal that doesn't publish garbage. Chen Gupta's breakthrough was recognizing that tired light could work if you don't use it alone, but combine it with expansion in a hybrid framework where redshift has two components, one from space, stretching as the Big Bang model says, and one from photons losing energy as Zwicky suggested. And by allowing both mechanisms to contribute, you can reinterpret observations in a way that extends cosmic timelines without contradicting key data, like the cosmic microwave background or supernova time dilation. Because the expansion component handles those observations normally, while the tired light component just tweaks distance and age calculations, giving galaxies more time to evolve. Gupta's hybrid model essentially resurrects tired light from the dead, but in a form that acknowledges and incorporates the successes of the Big Bang framework, rather than trying to replace it entirely. And he argues that for nearby objects, where light has only traveled a few million or billion years, the tired light contribution is negligible and expansion dominates. So local observations match standard predictions perfectly, but for the most distant objects visible to James Webb, where light has traveled over 13 billion years, in the standard model, the tired light effect compounds, becoming significant enough to substantially alter age estimates, and galaxies, we thought, formed 500 million years after the Big Bang might have actually formed 1 or 2 billion years later, giving them much more time to assemble their stellar populations and develop mature structures like spiral arms and central bulges. The mathematics works elegantly. In standard cosmology, a galaxy with redshift factor z equals 10 existed when the universe was 1/11th its current size, placing it extremely early and far away. But if half the redshift comes from tired light, the galaxy isn't as distant or early, it's somewhat closer and older, and for z equals 15 or 20, near the edge of what Webb can detect, the difference becomes enormous. And this effect is exactly what's needed to solve the impossible early galaxy problem, because those red monsters and massive structures that shattered the 13.8 billion year timeline suddenly fit comfortably in a 26.7 billion year universe where they had sufficient epochs to grow through normal processes. Critics immediately attacked the resurrection, arguing tired light was killed for good reasons that haven't changed, and bringing it back, even in hybrid form, violates established physics. And they pointed to the Tolman surface brightness test, which shows that in a static tired light universe, the surface brightness of galaxies should remain constant with distance, because while distant galaxies appear dimmer, their apparent size also shrinks, keeping brightness per unit area the same. But in an expanding universe, surface brightness decreases with distance, because recession causes both dimming and time dilation effects, and observations overwhelmingly favor the expanding universe prediction. Yet Gupta's response is his model isn't pure, tired light, static universe, but expansion plus a tired light correction. So it still predicts surface brightness, changes just not as extreme as pure expansion models. And the difference might be detectable with precise photometry from Webb and future telescopes. Other scientists point to constraints from the Oklo Natural Nuclear Reactor in Gabon, a geological formation where uranium ore underwent sustained natural nuclear fission reactions 1.7 billion years ago, creating a natural laboratory for testing whether fundamental constants have changed over time, and the isotope ratios left behind in the rocks constrain how much the fine structure constant could have changed to less than a few parts per billion. And if Gupta's varying coupling constants changed too much, they'd violate these Oklo constraints and be ruled out. But Gupta argues his proposed variation rates are well within observational limits from Oklo and other tests, and actually help explain other anomalies in atomic physics and quantum electrodynamics that have puzzled scientists for decades. The debate rages on, with some researchers finding Gupta's work intriguing and worth investigation, especially given the James Webb discoveries, while others dismiss it as a desperate attempt to avoid admitting we don't understand early universe physics. But one thing became impossible to ignore. After Webb started operating in late 2021 and began returning data in 2022, the 13.8 billion year timeline is breaking under the weight of observations, and something fundamental has to give. Either galaxy formation physics in the early universe was radically different from today, operating under rules we don't comprehend, involving exotic feedback mechanisms or unknown processes that violate our understanding of how gas cools and stars form, or the cosmic clock needs resetting to give structures more time to assemble through conventional physics. And Gupta boldly chose the clock by resurrecting tired light from its 90-year grave and combining it with Paul Dirac's evolving coupling constants. Proposed in 1937, Gupta constructed a framework that doubles the universe's age, solving multiple problems simultaneously. The red monsters get enough time to grow and mature. Methuselah and other ancient stars no longer exceed the cosmic age, creating impossible paradoxes. The Hubble tension between different expansion rate measurements eases because part of the discrepancy comes from not properly accounting for tired light effects, altering distance calculations. And the early universe timeline stretches from a frantic rush where everything had to happen impossibly fast to a more relaxed schedule where structures form at reasonable rates without violating known physics or requiring exotic new mechanisms. Whether tired light truly deserves resurrection or remains forever dead depends on future observations from Webb as it continues its mission through the late 2020s. Detailed measurements of surface brightness, evolution across cosmic history, more precise constraints on varying fundamental constants from laboratory experiments and natural laboratories like Oklo, gravitational lensing studies that can test how light bends in the early universe, and most importantly, the scientific community's willingness to seriously entertain alternatives to lambda CDM, which has become so entrenched. It's almost dogma. But one thing is certain: Zwickie's 95-year-old idea has clawed its way back from the grave and is demanding a second look, not because scientists are desperate or running out of ideas, but because the universe itself, through Webb's golden eyes, is telling us our timeline doesn't add up. And in science, that's how revolutions sometimes happen. Discarded theories resurrected when new data reveals the old paradigm can't handle reality anymore. And sometimes the answer to the future lies buried in the past, waiting for the right moment and the right evidence to return from the dead. The new reality, ushered in by the 26.7 billion year universe theory, is more than just a revision of a number. It is a radical transformation of how humanity views its cosmic roots, its history, and its future. And this transformation ripples through every corner of science, philosophy, and imagination, demanding that we question our oldest narratives and adapt our vision to a cosmos that is deeper, older, and more astonishing than anyone dared to guess. Imagine a universe in which the frantic deadlines that haunted previous generations of astronomers simply dissolve, meaning the red monster galaxies, once seen as impossible outliers, now fit comfortably into an expanded timeline, growing from modest beginnings into giants across 1 billion years or more. without any violation of natural law, and with generations of stars rising and falling in cosmic calm, not panic, their chemical richness and organizational complexity, taking shape through natural flows of matter rather than hasty bursts of turbulence. If the universe stretches back, not 13 but 26 billion years, then every event in cosmic history pushes back accordingly. The first stars ignite not in a race against the cosmic clock, but with ample space for gravity and cooling, to patiently mold pristine hydrogen into luminous spheres. The first galaxies gather their spirals and bulges through generations of mergers over tens of billions of years. And even the oldest star clusters, those ballrooms of ancient suns, become legacy archives of a gentler, more generous universe. In Gupta's extended framework, the epoch of reionization, the mysterious transition when the universe's foggy neutral hydrogen, cleared and starlight finally flowed freely, may take longer, allowing ultraviolet photons from the earliest hot stars to carve vast transparent voids in the cosmic haze at a graceful pace, culminating in a sky punctuated by mature galaxies of surprising richness rather than rushed, chaotic clouds. The central paradoxes of standard cosmology. Why do we find disk galaxies and supermassive black holes so soon after the Big Bang? Why do we observe stars that seem to predate the cosmos? Why does the universe look so organized at an age when chaos should rule begin to melt away, replaced by a narrative in which cosmic evolution follows a plausible stepwise path, and the impossible early galaxy problem becomes not a source of anxiety, but a signpost pointing the way toward a more accurate, honest timeline? In the 26 billion year scenario, the mysteries of dark matter and dark energy, which for decades have acted as placeholder fudge factors to make equations balance, face a new reckoning. For if tired light and changing physical constants can account for the observations once attributed to invisible mass or vacuum pressure, then maybe the cosmos does not hide as much in the dark as we thought, and instead the rules themselves have shifted with time. Light's journey, not quite so straightforward. The gravitational and electromagnetic forces that structure matter, not locked in stone, but evolving subtly as eons roll past. And suddenly, the need for exotic unknowns fades as the need for deeper understanding grows. Our picture of cosmic structure formation, the clustering of galaxies into superclusters, the filamentary cosmic web, and the yawning cosmic voids expands, with voids we measure today as billions of years old, revealing their true age as 2 or 3 times longer, every supercluster's story stretching into remote antiquity, forming through slow, graceful accretion as the universe matures in no hurry at all. Even life on Earth, arising fairly late in this new cosmic history, is put into sharper perspective as a young development in an ageless arena, suggesting not a universe rushed to deliver sentience, but one in which conditions conducive to life might emerge again and again in epochs we have not yet even glimpsed. And it invites renewed exploration of the multiverse concept, because with more time and more chances, the quantum fluctuations that might spawn bubble universes like ours become probabilistically more likely to pepper infinite spacetime with sister realities, each with its own laws and timelines. The new reality revolutionizes not just astronomy, but every discipline touched by the cosmic story: geology, paleontology, philosophy for timelines of Earth's formation, biological emergence, mass extinctions, and tectonic revolutions must now be referenced against a deeper cosmic backdrop, and what once seemed like ancient terrestrial history now looks positively youthful when compared to the true age of starlight or the long adolescence of the cosmos. In this vast new timeline, the search for extraterrestrial intelligence may take on greater urgency, because if intelligent civilizations had 20 billion years to emerge, Where are their artifacts, their signals, their warning beacons, or greetings? And this Fermi paradox deepens as our cosmic loneliness extends across longer and longer eras, raising new questions about the rarity or fragility of sentient life, the cycles of rise and fall, and the invisible histories written in worlds that lived and died before our sun was even born. Our most cherished cosmological concepts, like the arrow of time, the fate of entropy, and the emergence of complexity, all demand reevaluation, for an older universe allows for more opportunities for chaos to breed order, for star deaths to seed the next generation, for massive black holes to sculpt galaxies, and perhaps even birth new universes through enigmatic wormholes or white hole transitions, teasing the boundaries of current physics and urging theorists to hunt for quantum clues in deeper, older data sets. This is a universe where the cosmic microwave background becomes a less exclusive milestone, just one chapter in an unimaginably long book, and future telescopic missions may push ever farther to detect relic light from era even more ancient, perhaps revealing hints of what happened before the Big Bang. If such a question still holds meaning in a model where time itself sprawls across twice the previously imagined span, most profoundly, the new reality is a test of scientific humility and creativity, an invitation to embrace discomfort, to rethink cherished dogmas, and to recognize that the cosmos is not obligated to be simple, nor to fit the frameworks humanity builds when data are young and tools are limited, and instead, the universe smiles at our ambitions, misleads with paradox, and then, through remarkable breakthroughs and jaw-dropping discoveries, gently nudges us toward deeper truths. Whether or not Gupta's model will stand the test of future data, whether lambda CDM will be refined or replaced, whether tired light and evolving constants will become standard lecture fare or remain beautiful curiosities, the very act of reopening the timeline, of asking anew how old the cosmos really is, teaches us that the greatest wonders are not found in answers, but in the courage to keep questioning and in the awe that comes from realizing that our place in the universe is always, forever, just at the beginning of understanding. Ji, Ji. So here we are, standing at the edge of a cosmic revolution that could rewrite every astronomy textbook, every cosmology lecture, and every documentary about the universe's birth and evolution. And the catalyst for this upheaval isn't some exotic discovery from a far-flung corner of the cosmos, but something far more fundamental, a reconsideration of time itself, of how long the universe has existed, and of whether the 13.8 billion year timeline we've taught for decades is merely a halfway point in a story that's actually twice as long. We began this journey with the James Webb Space Telescope, peering into the cosmic dawn and finding red monster galaxies that shouldn't exist, massive mature structures packed with hundreds of billions of stars, existing just 500 to 700 million years after the Big Bang, when conventional models say only tiny dwarf systems should be stumbling into existence. And these discoveries didn't just puzzle astronomers, they shattered the timeline, revealing that either the physics of the early universe was radically different from anything we understand, or our cosmic clock has been running slow all along. Then we met Methuselah, that ancient star, floating just 200 light-years away in our own galactic neighborhood, a stellar patriarch whose age estimates keep coming back older than the universe itself, 14 or 15 billion years for a cosmos, supposedly only 13.8 billion years old. And while scientists tried to hide this paradox in error, bars and uncertainty ranges, the tension refused to go away, standing as a silent witness that something fundamental in our timeline was broken. Enter Rajendra Gupta, an adjunct physics professor at the University of Ottawa, who dared to ask the unthinkable question in July 2023, when he published a paper proposing that the universe is actually 26.7 billion years old, nearly double the accepted age, and Gupta didn't arrive at this number through wild speculation, but by resurrecting Fritz Zwicky's tired light theory from the dead and combining it with Paul Dirac's idea of evolving coupling constants, creating a hybrid model where redshift comes partly from space expansion and partly from photons losing energy as they travel across billions of light years, and by allowing fundamental constants like the speed of light and Planck's constant to vary over cosmic time, Gupta extended the timeline enough to solve multiple problems simultaneously. The red monsters get enough time to grow, Methuselah stops being a paradox, and the Hubble tension between different expansion rate measurements eases because we're no longer interpreting all redshift as pure expansion. This resurrection of tired light is controversial because the theory was declared dead decades ago, after failing to explain the cosmic microwave background and supernova time dilation. But Gupta's hybrid approach acknowledges these successes of the Big Bang model while arguing that a small tired light contribution tweaks distance and age calculations without contradicting key observations. And if he's right, then every major cosmic event pushes back in time, the first stars igniting later, with more time to form, early galaxies assembling through patient mergers over billions of years, rather than frantic rushed growth, the Milky Way's formation stretching across 15 or 20 billion years instead of 10, and life on Earth emerging, not 30% of the way through cosmic history, but merely 15%, making sentience seem even more recent and precious. The implications ripple through every corner of science, because if the universe is twice as old than dark matter and dark energy, those mysterious placeholders that supposedly make up 95% of cosmic mass energy might not be needed at all. Their apparent effects, possibly illusions, created by varying constants and tired light mechanisms, altering how we interpret gravity and expansion. And Gupta himself argued in follow-up work, published in 2024, that dark matter doesn't exist, a claim that if proven would revolutionize physics and vindicate the frustrated particle physicists who've spent billions searching underground and in accelerators for dark matter particles, but found nothing. The scientific community remains deeply divided, with critics pointing out that tired light was rejected for good reasons, and that Gupta's model must still explain surface brightness, evolution, gravitational lensing patterns, and the detailed structure of the cosmic microwave background, while defenders note that the James Webb discoveries demand we at least consider alternatives to lambda CDM, because the 13.8 billion year timeline is clearly breaking under observational pressure, and some researchers like Lior Shamir have published complementary evidence supporting tired light predictions, though mainstream cosmologists argue the early galaxy problem will eventually be solved through better understanding of star formation and feedback processes without requiring such a radical timeline revision. What makes this moment in history so electrifying is that we're living through it in real time, watching as the James Webb Space Telescope continues operating through the mid-2020s, finding more impossible galaxies, more supermassive black holes in the early universe, more structures that challenge conventional models, and future facilities like the extremely large telescope in Chile and the Nancy Grace Roman Space Telescope will test Gupta's predictions by measuring galaxy properties at extreme distances, checking surface brightness evolution, searching for evidence of varying fundamental constants in distant quasar spectra, and looking for the earliest stars to see if they appear at higher redshifts than lambda CDM allows. Whether Gupta's 26.7 billion year universe survives this scrutiny or falls apart under detailed testing, the very fact that we're seriously reconsidering such a fundamental question demonstrates the vitality of science as an enterprise that never stops questioning, never accepts dogma, and always follows evidence, even when it leads to uncomfortable places that force us to admit we might have been wrong about something as basic as how old everything is. The philosophical weight of this potential revolution is staggering, because for nearly a century since Hubble discovered cosmic expansion, we've built our entire understanding of existence on the assumption that the universe began 13 to 14 billion years ago. And if that number is wrong by a factor of 2, then what else might we have wrong? What other constants aren't constant? What other laws might change over time? What other mysteries hide in plain sight, waiting for the right observation or the right theory to reveal them? And it forces a humility on human civilization that sometimes grows too confident in its knowledge, forgetting that every generation thinks it has the answers until the next generation discovers they were building on shaky foundations. For those of us who gaze up at the night sky and wonder, the 26.7 billion year universe offers a cosmos that is deeper, stranger, and more forgiving than the compressed timeline we've lived with. A universe where the rush to form galaxies and stars becomes a patient evolution, where ancient mysteries have twice as much time to unfold, where the arrow of cosmic history stretches so far back that our entire human story, from the first stone tools to the James Webb Space Telescope, occupies less than 1/10,000th of universal history, making us simultaneously insignificant in scale yet miraculous in our ability to peer back across such gulfs of time and actually figure out how old our cosmic home truly is. The textbooks will need rewriting, not just the astronomy sections, but the physics chapters on fundamental constants, the philosophy discussions about time and creation, the theological considerations of cosmological origins, because every field touched by the question of cosmic age will need to adapt, and future students might look back at our 21st century confusion the way we look back at 19th century debates about the Earth's age, when physicists thought it was only millions of years old, based on cooling calculations before radioactivity was discovered, proving the planet is actually billions of years old. And just as that revelation opened new vistas of understanding about geology and evolution, so too might doubling the universe's age unlock new insights about structure formation, the nature of time, the possibility of earlier epochs we haven't detected yet, and perhaps even hints of what came before the Big Bang. If such a question makes sense in a cosmos where the rules themselves change, we thought we had it figured out. We thought 13.8 billion years was solid bedrock, but the universe just smiled at our hubris and whispered through the golden mirrors of the James Webb Space Telescope that reality is always deeper than we imagine, always more mysterious than our equations capture, always ready to surprise those brave enough to keep looking, keep questioning, and keep following the evidence wherever it leads, even if that means admitting we've been reading the cosmic clock wrong all along. And in that admission lies not failure, but the triumph of science, the willingness to evolve, to adapt, to rewrite the textbooks when the universe demands it, because the greatest discovery isn't finding the right answer, but finding the courage to ask better questions. And right now, standing at the edge of 2025, with more data pouring in every month from Webb and other telescopes, we're asking the oldest question in the newest way: how old is everything? And the answer emerging from the cosmic dark might just be far older than you ever dared to dream.